For any given element, the ionization energy will increase as an increasing number of electrons are being removed. Because remember, when you remove an electron, the effective nuclear charge on the remaining electrons will increase because there is one less electron to distribute this nuclear charge among. However, we do have some elements that behave slightly different in certain levels of ionization. Take, for instance, the second ionization of sodium, the third ionization of magnesium, and the fourth ionization of aluminum. All are much higher than their previous ionization energies. Thus, we can conclude that something else must be taking place. The answer, of course, lies in the element's electron configuration. So let's look at their electron configurations to see if we can identify a pattern. Sodium's atomic number Z is equal to 11. Therefore, its electron configuration is 1s2, 2s2, 2p6, 3s1. Magnesium's atomic number Z is equal to 12. Its electron configuration is 1s2, 2s2, 2p6, 3s2. Aluminum's electron configuration, Z, is equal to 13. Sorry, its atomic number, Z, is equal to 13. Therefore, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. Now, after sodium's first ionization, its electron configuration will be that of neons, 1s2, 2s2, 2p6. After magnesium's second ionization, it will have an electron configuration also equal to that of neons, 1s2, 2s2, 2p6. After aluminum's third ionization, it will also have an electron configuration equal to that of neon, just like sodium and magnesium. So the first ionization of sodium, the first two ionizations of magnesium, and the first three ionizations of aluminum all leave us with the same electron configurations, 1s2, 2s2, 2p6. So I think we've identified the root cause of the three higher than normal ionization energies. When each of the elements, sodium, magnesium, and aluminum, lose their valence electrons, all three of them have identical electron configurations equal to that of neon, which is the noble gas element at the end of period 2. The electron configuration, 1s2, 2s2, 2p6, represents the noble gas core for sodium, magnesium, and aluminum. And this factor is the root cause of all three higher than normal ionization energies. The removal of an electron from an element in its stable noble gas core requires significantly more energy than the removal of a given element's valence electron. And under normal circumstances, chemical reactions supply enough energy for the removal of valence electrons, but not enough to remove an electron from an element's noble gas core. We can therefore conclude that removal of an element's valence electron and the resulting noble gas core is representative of the common cations that are formed by most elements. Electron affinity. Ionization energies are used to describe the formation of cations. In chemistry, we use a different term to describe the formation of anions. The term electron affinity is used to describe the energy change that is associated with adding an electron to an element in its gaseous form. For instance, chlorine can pick up an electron and form a Cl- ion, and in the process it can release, or it will release, 349 kilojoules per mole. We can write the process as follows. Chlorine, its abbreviated electron configuration is neon 3s2 3p5. If chlorine picks up an electron, its resulting abbreviated electron configuration will now be bracket neon 3s2 3p6. And when chlorine picks up this electron, the enthalpy associated with the process is negative 349 kilojoules per mole. So it's an exothermic process. When chlorine picks up an electron, it releases 349 kilojoules per mole. When it picks up this electron, its 3p orbital is now completely filled with electrons. Interestingly, unlike ionization energies, which are always endothermic, meaning it requires an energy input, ionization energies always require an input because you're removing an electron. You're removing an electron that's attracted to a positively charged nucleus, so it makes sense that you have to input energy. But the first electron affinity of an atom may be endothermic or exothermic. After the first electron affinity, though, subsequent addition of electrons will always be endothermic, and this is simply due to the addition of a negatively charged particle to a negatively charged ion. When you've added an electron, you've added a negative charge to the atom. Therefore, adding more negative charge will be an endothermic process. You will have to input energy. But the first addition can be endothermic or exothermic. So subsequent electron additions to a negatively charged ion will require an energy input because you're overcoming the electrostatic repulsion between the electrons and the ions. So that's an interesting phenomenon. Ionization energies are always endothermic. The electron affinities may be endothermic or exothermic for the first addition only. The general trend in electron affinity is more or less the same as the trend for ionization energy. Atoms with smaller atomic radii and a higher effective nuclear charge, remember a nuclear charge is positive, tend to have a higher electron affinity because of the positive charge. It is attracted to electrons. Therefore, we can conclude that as we move from the lower left to the upper right of the periodic table, electron affinity will increase. Now, this figure summarizes the three periodic trends we have discussed so far, which are atomic radii, ionization energy, and electron affinity. So, moving from left to right on the periodic table, we expect an increase in ionization energy and an increase in electron affinity. We expect the exact opposite for atomic radii. So we can say in moving from right to left, we would expect an increase in atomic radii. Likewise, moving down a given column on the periodic table, we would expect an atomic radius increase. The opposite is true of ionization and electron affinity. As we move up a column, we expect both electron affinity and ionization energies to increase. So large atomic radii, small ionization energy, and low electron affinities are all what we would call metallic characteristics. High electron affinities and high ionization energies and small atomic radii are all what we would call non-metallic characteristics. Now, I don't want to discount all of the generalizations I made on the figure on the last slide, but unfortunately, electron configurations tend to complicate the electron affinity trends even more so than ionization energy trends. For instance, noble gases have ionization energies, but because their p orbitals are completely filled, they have zero electron affinities. Additionally, alkaline earth metals also have ionization energies, but have essentially no electron affinities since their outer s orbital is filled. More complications appear when we consider less representative elements such as gold. Gold has an electron affinity higher than any other element besides the halogens. The halogens have the highest electron affinity by far on the periodic table. But the electron affinity for fluorine is actually lower than we would expect, and this is due to its size. Fluorine is, in terms of atomic radii, the smallest element on the periodic table, and it's too small to accommodate additional negative charge without accompanying significant electron repulsion. Nonetheless, fluorine still has a very high electron affinity, but it is actually second to chlorine. Chlorine has the highest electron affinity of all the elements on the periodic table. Now, large negative electron affinities indicate that a very stable negative ion is formed, where a small negative number indicate that a less stable negative ion is being formed. So in this table, we've got electron affinities for the main group elements, group 1A, 3A, 4A, 5A, 6A, and 7A, the halogens. We said that the electron affinities for 2A and 8A, the alkaline and the noble gas elements, are essentially zero, so we don't show them. Now, if we look at the general trends, moving down a given column, the electron affinities more or less decrease. They get smaller because the atomic radii are larger and the effective nuclear charge tends to stay the same. So you've got to overcome more of an electron-electron repulsion. Additionally, the nonmetals tend to have greater electron affinities than the metals. Here, metals tend to have low electron affinities and tend to form cations, whereas nonmetals tend to have higher electron affinities and tend to form anions. So let's sum up the general trends in electron affinities. The general trend is that nonmetals tend to have high electron affinities and will tend to form anions. This is because they have high electron affinity, but a low ionization energy, meaning it's difficult to remove an electron from a nonmetal. Metals, on the other hand, have very low electron affinities and tend to form cations. And this is because they have low ionization energy, meaning it is easy to remove an electron from a metal. So, nonmetal, high electron affinity, high ionization energy. Nonmetals like electrons. They don't like to lose electrons. A metal has a low electron affinity and a low ionization energy. Metals do not tend to gain electrons. They don't have a particular affinity for electrons. They have a low ionization energy, meaning it is easy to remove an electron from a metal. One can actually write electron configurations and draw orbital diagrams just as one can do for atoms and cations. The additional electrons that are added to an atom are added according to the building up or Aufbau principle, meaning that the subshells with the lowest energy level will fill first and build up accordingly. So let's do oxygen as an example. Oxygen, its atomic number in its ground state is equal to 8. So its electron configuration is 1s2, 2s2, 2p4. And we can draw its orbital diagram as follows. 2 electrons placed into the 1s orbital, 2 electrons placed into the 2s orbital. Then let's draw the 2p orbital. 1 electron, 2, 3, and 4. Now, if oxygen were to pick up an additional electron, its atomic number is still equal to 8, meaning it still has 8 electrons, but it now has a negative charge because it picked up 1 electron. So let's draw its electron configuration. 1s2, 2s2, 2p5. So when oxygen picks up this electron, it will be placed into the 2p orbital. We can draw its orbital diagram as follows. Now its 2p orbital, instead of having 4 electrons, it now has 5 electrons. 1, 2, 3, 4, 5. But it still looks like it's got room for 1 more electron. So oxygen, remember, in its ground state, its atomic number is equal to 8. So its electron configuration is 1s2, 2s2, 2p4. And its accompanying orbital diagram is drawn as follows. So it's got 1, 2, 3, 4 electrons in its outer 2p orbital. Now, in its outer 2p orbital, it actually has room for 2 electrons. So if oxygen were to pick up 2 electrons, its 2p orbital would be filled, and its overall charge would be -2 because its atomic number Z is still equal to 8. It still has 8 protons, but now it's got 10 electrons, so its overall charge is -2. The resulting orbital diagram can be drawn as follows. Its 1s and 2s orbitals, of course, stay the same. But the difference is in its 2p orbital. It now has 6 electrons in its outer 2p orbital. 1, 2, 3, 4, 5, and 6. So the oxide ion, O2-, is now isoelectronic, meaning it has the same number of electrons to the noble gas element neon. Once an atom achieves an electron configuration that is identical to that of the noble gas element, at the end of the period, its electron affinity becomes 0, or nearly 0. It still has some electron affinity, but it's next to nothing. And this means it can no longer accommodate any more electrons. Its orbitals are completely filled. It has filled its valence shells and now has a very stable electron configuration. So in essence, the main group elements, this is for the nonmetals, will only gain electrons until their valence electron shells are filled. And this is an important theme that we will revisit and talk about when we talk about chemical bonding. So let's wrap things up. In this lesson, we wrapped up talking about ionization energy by naming a few exceptions to the trends, and we talked about what can be considered to be the opposite of ionization energy. The opposite of ionization energy is electron affinity. Now remember that like ionization energy, electron affinity tends to increase from going from left to right and moving up the periodic table. Electron affinity, like ionization energy, is greatly dependent on the element's electron configuration and on the effective nuclear charge the atom's nucleus has on the surrounding electron.